My name is Stefan. Mine is actually a lightning talk, so it's just hopefully 5 minutes. Just a very brief update to the people that actually know what OpTiMSoC is, a brief introduction, what it is, then what the updates are, and finally how you can use it actually. So OpTiMSoC is a project from the TU of Munich, where I'm from. Actually, I graduated, or I'm about to graduate my PhD from there, hopefully sometime soon-ish. So I left 2 years ago, actually. I'm in the process of getting it done, and it's like this is part of the outcome. And Philip, who's also with me, was a former student of mine, is now conducting it at the university, and yeah. What is it? It's like, if you know, like tiled many-core system on chip nowadays, like you can find a very regular structured if you want to organize like gazillions of cores. We are more speaking of, let's say, like 256, like this class that you can see nowadays also commercially. And what we needed it for is kind of like a research vehicle, right? And if you want to do research on such platforms, you have to build them on your own, apparently. At least when we started this, like 2009 or 2010-ish. And so my research was in on-chip, high-speed message passing on like application level, like user-to-user communication. Most of those platforms are usually focused on bare metal applications, so it's kind of like more in future directions. It was pretty much focused on FPGA prototyping because of commercial, like cost reasons in the end, apparently. And if you look at it, it's based on a network on chip, like packet switch networks that interconnect so clusters called tiles of processing resources, which are like usually multi-processor resources nowadays. Like you can often find like 4 to 8 cores in one cluster, use shared memory programming inside, and then use some other programming model globally. At least that's the kind of direction that we are thinking and using. And so that's the main resource. It's called compute tile in our nomenclature. We have like 4 tiles sometimes. More often it's only 2 maybe. And you have some local SRAM quite often, either at least as caches, of course, but also as some like scratchpad memory that your operating system uses to do some swapping and stuff like that around there. And in my context, also like for doing message passing communication, like getting the data around on the chip, right, next to the processing. And we have something called a network adapter, and that's the kind of research that we do usually. It's around like how to communicate between those tiles now, how to do this efficiently, not only sending out raw packets, but also doing message passing, like you know from MPI, from supercomputing on such platforms. And yeah, as I said, like I was researching on doing this efficiently, and you have some other resources there, like you have some global memory access, like some DDR access, and you have some I/O. Also, part of the research that we did is if you have like I/O now and you want to have some kind of virtual connectivity, like having virtual NICs sitting on the outside, like network interface cards, and directly communicating with like user level tasks, and have some kind of virtual channels right from the outside into your tiles. That was the kind of research that we did there, and that's kind of the background. And in the last year, I did a major rewrite of the network on chip, which is a very simplistic one. Like this is how you would write it if you are in your first year. No, this is how you would write it if you knew like 7 years of digital design and then write it in your first year of your studies. Like 16 lines of Verilog that are the effective network on chip stuff. All the other stuff is just wiring, right? It's a pretty composable infrastructure that we have now. Like you could experiment a lot with like physical networks, virtual channels and networks, stuff like this. Clock domain crossings is pretty interesting topic apparently in this context, and how to assign stuff, right? And yeah, as I said, like currently I'm getting out all the stuff that I have in my private repository about message passing to the public repository. Like once my thesis is out in the world, I want to have the code out in the world apparently. Currently I'm holding it back a little bit. What we had this year was a Google Summer of Code student and the FOSSI Foundation who ported Linux to it, not in a way that you would now imagine, like there's a global Linux instance running on it, which is kind of a sanity problem that you reach pretty soon. But instead we have this nomenclature of a host tile that is like a connectivity title. So you log into the host title and you can just work with this platform as standalone and not as some kind of accelerator. That's pretty interesting for demonstrations for us. So we have Linux booting on it, and you could just like from Linux start applications and on the tiles, right? So you could say I want to start tasks there and there, and that's kind of the idea. And most importantly, what we did last year was a lot of code infrastructure updates, like cleaning up my system, Verilog coding style, adding comments here and there, adding actual documentation that also like builds and like describes what actually in the code is and stuff like that. And so we switched to full FuseSoC support. Maybe we will hear about it next days, I don't know. Yeah, FuseSoC is something that you might need if you want to build digital systems. And so if this interests you, like this is our website, OpTiMSoC.org. We spent considerable, like I think we spend more time on the website and documentation than code actually, which is good, I think. At least people tell me this should be good. What we have is like automated documentation builds, so you can have for the different branches and releases, you can see documentation. We have a tutorial, and we are somehow proud now that it actually works, the tutorial at all times, because it's automatically tested. So we have PyTest-based continuous integration that actually runs the tutorial and checks if it still works. So at least this part works. Most other stuff breaks usually, but that's like normal, it's continuous integration, right? So like jump into the tutorials, it's pretty straightforward. You just need Verilator to start with. That's the straightforward thing, just learn a little bit. Of course, there's no like tutorial about like how to do something meaningful with it, because I yet don't know, to be honest. We have two FPGA boards. One is the like standard digital and like student board, the Nexus board, which you can use with WebTalk, no, what's called Webpack. And the other is the large ultra-scale Xilinx board, where we actually want to run on larger systems now. In this context, pretty interesting is like probably the spin-offs that we created. In the beginning, it was like a large project, and we had like plenty of students working on bits and pieces. But after some time, we found that some stuff may be reusable. One of this is this generic logic interface project, how we call it, glib.io, which is like the idea there is that you have a FIFO interface on the host side, and you have a FIFO interface on the target side, plus a reset pin. And this is like a standardized interface, and we try to encapsulate everything we can find in terms of physical transport, which is like UART, USB 2, USB 3, PCI Express, whatever, and try to encapsulate it in just the same interface so that we could reuse our same design on different platforms, at least in the communication part. And the communication part here is OpenSoC debug, which is our trace-based debug infrastructure. It's mostly trace-based because there's also some kind of research that we do about efficient tracing and trace like agglomeration on chip, stuff like this. There's a talk tomorrow evening, I think, from Philip about OpenSoC debug. So if you're interested, that's probably like the reusable parts of OpTiMSoC that we like put in separate projects that may be of interest to you. And yeah, we have USB 3 working now finally, the Cypress FX3 stuff, which is more pain than expected. But now we finally have the VCU 108 at full speed, 100 megabit per second. Megabyte per second for tracing, which is good because before, like, you were mostly stuck to simulation if you want to get a full trace of everything, because on the Nexus you are bound to 12 megabaud UART, which is okay for one core, but if you have a second one, it just dies. Okay, so more than I expected, but that's my lightning talk. Thank you very much. Any urgent questions? Otherwise, we can take them offline. Yeah? No, we didn't. So here and there we did some minor tweaks that we know work better on FPGA. For example, like for buffers. So if you have a FIFO, you could use the shift register part of the Xilinx layer. So we use Xilinx FPGA, so we know like how to write code that synthesizes to a shift register. Yeah, but there's not much much in this direction here. Like the NOC, as I said, like the NOC itself is so simple you can't optimize anything to anything, I think. It's just like, it's a lookup table which usually synthesizes logic, right? And you don't want to use SRAM block for this one. And yeah, so we most, like, as I said, like the most thing is the FIFO, I think, where we did some FPGA specific stuff. But not like some if-devs, just like, if you write system Verilog in a certain way, the synthesis tool likes it and generates the proper shift register out of it. Yes.
So you listed 2 supported FPGA boards there.
Yes.
How big are your arrays, your network matrices on each of the boards?
Currently, it's like 2 times 2. Because that's the one that we use on the smaller one. And if you know the turnaround synthesis time of the ultra-scale stuff, we stick with this currently. I don't know if you did an experiment already. Philip can tell you later. I would say it's probably like in the ranges of 128 cores. Not arranged in a too big, because then, like, depending on the NOC channels that you need, it can sum up easily.
128 cores on
the larger one, yeah. On the smaller one, the limit is 12 cores. So I have 12 cores in a 2 times 3 layout where one of them is memory. So it's like, one is I/O. Yeah, I have to look up. It's 2 cores in 6, yeah. So it's 12 cores, yeah.
Thank you very much.
Oh yeah, it's open RISC cores, by the way. I forgot to mention.
Why isn't it RISC-V? Why are you
So like, so actually, so the question is, why isn't it RISC-V cores? So the answer is, it's not yet RISC-V cores, probably. So to be honest, I'm still struggling to find a proper replacement for the MO1KX core. There's like a gazillion of RISC-V cores, but none of them is like a 32-bit multi-privilege. Like the privilege level is the problem in RISC-V usually, I think, in implementations. There's many 32-bit implementations, but it's hard to find one that is like perfectly comparable to MO1KX. I stand corrected. Clifford already looks like he would want to argue this argument, but and it's open source. Like, you can contribute if you want to. Yes.
Do you provide some test benches or performance tests? This would be very helpful.
Yeah. So we only do functional tests, not performance tests. So like the test benches we do is like, does it still work? So it's like, we are still in this phase where the mindset is, do we break it, and not how much better do we do it now. I would say like, so we have everything in place. So we have like, that's also something I added last year. We use this common trace format that the Linux kernel tracing stuff is with, like, as our trace format. So you could easily use all this stuff to do your measure. Like, I wrote just a set of Python scripts around it to do my graphs for my thesis, for example. And they are the same for simulation, and they are the same for my system level simulation, and the same for FPGA-based systems, which makes it pretty handy. This is more like an OpenSoC debug thing, apparently, not OpTiMSoC itself. But we don't have like we have a few tests that do like ping pong, or like just like hurricane traffic patterns, stuff like this. But we don't have like a large set of applications that we run under usually. Yep. The microphone? Do we still have it? Andre.
My apologies if this is a repeat question from some time ago. Do you have the ability to not just carry data between the cores, but actually program code itself?
Yes. So that's also part of my thesis, actually. So we have the ability to move, you can do like migrating tasks. You can start new tasks. That's like the two things that we can do. Starting is pretty straightforward. So you just like forward like a trigger, and then it fetches something. But we also have some migration, and there, like my thesis part is actually about the migration of the communication part. So because that's pretty challenging if you, like it's like with a virtual machine in a data center. You have a lot of open communication channels, and they are not like bound to some bare metal simple things, but there's like a larger stack in between, and this has a lot of buffers usually, or like ideally not too much buffers apparently, but it has some, and so you do some kind of cold migration or hot migration stuff, and that's kind of the stuff that I explore for my thesis. So you migrate a task bit by bit, so you until you don't have any changes in your TLB anymore. Then you just switch over, and in between you have the data already ready on the communication channel. So you start into dual casting mode while you're migrating. You coordinate like which packets to throw away, and then you do the hot switch over. So you have like virtually no downtime in switching. That's the idea there.
So, I've got two more questions.
Yes.
You mentioned about privilege levels. So we're talking user, super user.
No, only two. Like that's enough for me. But I want to have like a user and supervisor level. So that's the idea that.
Okay. And the last question: have you actually had a chance to run a Mandelbrot set on your array?
No, not yet. But it's on my to-do list. Yeah, I still have a few like simple applications that I want to run. Mandelbrot is one of them. Yeah.
Thank you.
Okay, then. Thank you very much.